Hey guys, it's Mr. Sheeline here. So we're gonna shift things a little bit when it comes to doing the notes here for you guys. So just because now that we're getting into projectile motion, the problems are are going to be a bit more complicated, and because they're a bit more complicated, they're gonna need more space, or I'm gonna need more space to write them out. I'm gonna need more time, and I'd rather not have like an hour and a half video that only contains like 15 minutes of notes. So this is just going to be running through the notes. I'm going to be skipping over the check your understandings. I'm going to be doing a separate video on the check your understandings. And that's going to be in a little bit different format. It's not going to be, on the Google Slides. So again, just so that you don't have to sit there for an hour and a half and wait to go through all the notes or have to worry about fast forwarding, I'll just make two separate videos. So all right, let's just go right into it. So we were working on, two-dimensional motion. We didn't really stick a whole lot of time with it, just because it's for the most part just a bit more trigonometry, or just is trigonometry. It's geometry. It's not terribly difficult. The only thing that we need to practice more or less is to practice the distinction between, x-axis variables, y-axis variables, okay? And the reason that we have to make distinctions between them is more or less just the idea that they are, when we're using vector quantities, we have to separate vector quantities into the groups that they're assigned to by the directions they're traveling. So for instance, in the case of this, we need to focus on horizontal, in this case with projectile motion, when we're trying to find specific variables, like say velocity or acceleration, we for the most part only use and pay attention to variables that are part of the horizontal axis or the horizontal plane. And if we're trying to find stuff for the vertical plane, we have to use variables within the vertical plane. So that's what we have to know before we're coming into this, or at least just that much, and then we can get right into it. So let's just do that. All right, so projectile motion. So the most common example of an object moving in two dimensions that's projecting, or a projectile, this is the most common example. Moving in two dimensions where only the force of gravity and the air resistance are acting on it. Now, I'll just have you know that for the most part, the only thing that's affecting these guys is gravity. Most, if not all, questions we ignore air resistance, and that's going to be true from now until the end of the year. Air resistance exists, yes. Do we need to know that it exists? Yes. Do we really have to overcomplicate things when we're just trying to first learn this stuff and add air resistance to everything, and then add a whole 5-minute step to finding your more accurate numbers? No. We don't need to do that. So in most cases, again, like 99.9% of cases, we just ignore air resistance. Okay. So an example of a projectile, this will be a baseball, cannonball, snowboarder getting air, a firearm firing a bullet. What else? Throwing a rock, shooting an arrow. Just anything that you can by just standing there, anything you can basically toss, push out, blow, or fire. That's what we're going to be focusing on. Okay. Oh, well, shoot, I didn't mean to make that happen, so I guess you saw it, but whatever. Okay, so the idea here is for you to see, what do you see? What do you think between these two graphs? And it wasn't supposed to show the answer, but whatever. But anyway, so what do we see? Well, what do we see? We see that these two balls reach the lowest position at the same instant, even though one was projected horizontally. Both had an initial vertical velocity of 0, and both experienced free fall. Okay, so more or less all this shows is like what I showed you the other day, is that like with the ping pong ball and the what's it called, and that big ball bearing. At least for one of my classes, I showed this. And I've got a demo for you. But when we come back in, I've got a demo for you. just to show you like, oh yeah, like this isn't just on paper, like this is in real life. So yeah, these two balls reached the lowest position at the same instant. And why? So let me ask you this: why did they reach the same position at the same time? Why did they both, let's say, hit the ground at the same time? Okay, think about it. Well, the answer should be pretty obvious. The answer is, well, gravity, regardless of the mass, gravity is affecting these guys exactly the same way. Their initial velocity is 0. They're both dropped. If they're both dropped at the same distance or at the same time, at the same distance from the floor, they will hit the floor exactly at the exact same time. Okay, and we know this is true, with most things in life, and that we can drop at relatively short distances, and we know that's true, especially in a vacuum. The only I guess snag you would have, the only snag you'd have is air resistance, and that's for the most part why we ignore air resistance. Is that it's a very particular case you would need to calculate it, and for the most part, if we're shooting, dropping, comparing things falling to the ground, they're relatively speaking about the same size anyway, or at least a lot of times we don't worry about two different items. So moving at the same rate from the same distance, dropped at the same time, or thrown at the same time. So we just don't bother with air resistance in this case. So yeah, gravity, the answer again is just gravity affects both at the same time, at the same rate, regardless of their opposing masses. Okay, so here's some examples, just more examples, visuals of the kinds of projectile motion that we'll be dealing with. So, and I was hoping my pen would be here. Let's see. No, go back. We'll see. Pointer. Oh, that's kind of cool. How does that? Okay, I guess I can't do that. I'm trying to figure out my pointer here. I guess I'm going to have to pause this real quick because my toolbar is not up because I wanted to draw a little bit. So here, give me a second. There it is. Okay, let's try this again. All right. Sorry about that. I just wanted my little pen here just so I can show this. It's just for this. So here are some types of motion. So with projectile motion, we're going to be focusing in on for the most part, 2 to 3 different kinds of, relatively speaking, 2 or 3 kinds of projectiles, or at least patterns. Now, we're going to talk about the shapes that these make in just a second, but just kind of looking at these, this is probably going to be the most common. Is going to be person or thing here will project object at some angle, with some velocity here. And we're going to track, the pattern in which it is being projected, and we're going to be able to calculate the distance between the point at which it was thrown to where it landed, and also the maximum height in which it reached, typically in the middle of its projectile. This one is pretty much the same. It's just a little bit tighter. I'll just say to make maybe a correction, or maybe not so much a correction, but a differing kind of idea, is that we will be working with this. And this is, again, this right here is pretty much the same as this. But what we will be working with is that we will be working with balls being thrown straight up in the air and then balls coming straight down, which we've kind of already been doing anyway in one-dimensional motion. So we'll still be working with that. And we've been working with this already over here. We've been working with dropping, things off of buildings, dropping them, and for the most part, we've also been working with this too. It's just now we're going to be able to know exactly, okay, where was it thrown horizontally? What's the distance it travels? Okay, what height was it thrown from? What's the maximum height it reaches? And we can then calculate the time it takes overall. We can calculate, what's the average velocity, or what's the final velocity for the entire, God bless it, what's the final velocity for the entire motion, that sort of thing. Here, let me pause. I need my toolbar again. Okay, Alt-T. Control-T. Yeah, it's not Control-T. Sorry. I love Screencastify, but sometimes, man, oh, there it was. There it goes. Okay. And that's not what I wanted. Okay. And then another kind of motion that we're going to do is going to relate to that cliff idea right there. It's going to be more like, you know, if we like continue the cliff here. If we continue the cliff, it's like, let's say this person here actually tosses that ball this way and it travels like over the cliff, past the cliff. Okay. We'll be asking, okay, what's the horizontal distance from here to where it lands? What's the maximum height it reaches from the bottom of the cliff to the top of its projection? So we're going to be, working on that, and excuse me. And that's going to be another kind of projectile that we're going to be working with. And that, for the most part, is going to be it, the types of projectiles. So, okay, so let's continue. Oh, and I got to erase all that. Sorry. Okay. Okay, so a force is not required to keep an object in motion. And so what I want you to do is I want you to think of as if something's moving through space. So meaning, if you've got, and you'll see this in the examples here, in the check your understandings. But when we're working with, remember, like I said, when we're working with projectile motion, with two-dimensional motion, we have to keep the axes separate. So what we're going to have, horizontal motion, and we're going to have vertical motion. Okay, vertical motion, yes, does affect the horizontal motion of a particular object, but that's where this comes in. That's where the hypotenuse comes in, right? But when we're looking at and we're talking about, like, say, something was projected, it was like, let's say a hockey puck was hit at a horizontal rate of, let's say, 5 meters per second. Well, that 5 meters per second in the horizontal doesn't change. The only time it would ever change is if this were to be true. And in order for that to be true, that would mean then this guy right here would be accelerating. In this case, it would be increasing. Now, obviously, yes, there's air resistance, but in real life. But remember, we're forgetting about air resistance. So the idea is going to be that something hit vertically is going to only stop something hit horizontally at a particular rate is only going to stop when it hits the ground due to the vertical acceleration known as gravity. Okay, that's as of right now, that's what we're going to be doing. Excuse me. And so yeah, the only time this up here is going to be true is, again, if there's an explicit it explicitly talks about acceleration or deacceleration in the horizontal plane or whatever plane we're talking about. But yeah, a force is not required to keep an object in motion. Okay, and that statement will make more sense as we continue, or it should. Okay, so then yeah, forces cause acceleration. I made that note already. In the case of projectiles, there's only a downward force and therefore a downwards acceleration, neglecting air resistance for now. Okay, for the most part, for the whole year, realistically speaking. Okay, so consider a cannonball shot horizontally. So we're trying to kind of picture this real quick. So suppose gravity would be quote unquote turned off. So what would the motion of the cannonball look like? So I want you guys to take a second here. I want you to pause the video and I want you to really think, if we just turned off, if you had a cannon, if you got the cannon here and it shoots a cannonball, okay, so if it shoots a cannonball here out of the cannon, what kind of motion is this going to exhibit? What will the pattern of motion look like? So I want you to pause the video. I want you to figure this out for yourself, maybe draw your own picture, and then play the video again and then see what I talk about, okay? Okay. So let's say that we turn off gravity, and let's say we shoot a cannon off of cannonball out of this cannon, what would happen? Well, for the most part, whatever velocity, whatever rate, whatever kind of force is applied to it, again, when we ignore air resistance, okay, we're going to just have a continually moving object, exactly at the same level, exactly at the same rate, exactly on the same plane. As long as nothing hits it, it's going to continue to move on that plane. Okay, and that's why I say think of this in space. Like that's why what is so because in space, as in you don't have an atmosphere and you're not terribly being pulled by gravity, or at least affected by gravity at a substantial degree like here on Earth. Anything that has a force applied to it will continue to move in that direction. And we get into that. That's Newtonian right there is part of Newtonian's law, or Newton's laws. And we get into that after this. But all you have to know now is, like, without gravity, this is what our gravity-free path would look like. So without it, an object in motion will continue in that motion with the same speed and in the same direction. Okay, now let's turn it on. What do you think? So pause the video, think about what will happen. Okay. So will gravity affect the cannonball's motion? Obviously, we should be able to think of this. Of course it will. Okay, so here is the projectile's parabolic trajectory. Okay, so that was that word, parabolic. Okay, that's what we saw on a couple of slides before. Now we should have already known this. So with gravity, projectile falls below its inertial path. We'll get into inertia later on. Gravity acts downward to cause a downwards acceleration. There are not horizontal forces needed to maintain the cannonball's motion. This cannonball is moving horizontally at the same rate on the horizontal plane. The only difference is that now we have an acceleration. We have a force being applied to this, moving it in the downwards direction. Okay. So gravity acts downwards on the cannonball, affecting its vertical motion only. And then gravity causes a vertical acceleration downward. So this is going to be a super duper important integral idea to solving for these different problems in projectile motion. Okay, so let's take a look at this guy right here. So this is just a GIF that'll keep replaying. So, and I know, yeah, you see that the thing it's coming out of, it's supposed to be a cannon, like over here. This is supposed to be a cannon, and I know it looks like a weird lion-looking frog thing with its mouth open. Just understand that that's just it's supposed to be like a pixelated, like, little bundle of clouds that are supposed to come out as the cannonball is shot. So that's why it looks so goofy. So anyway, so let's pay attention to the components. What do we notice? Okay. So if I could stop it, let's look at this. Well, first, let's actually talk about the direction. So as you can, in the shape. So as you can see, it's like we mentioned, it's that parabolic shape. And that parabolic shape, remember, is your bell curve shape. That is for the most part, we'll just call it the bell curve shape. It's the parabolic is the bell-shaped curve that has equal sides to both sides. Okay. So if you were to cut it in half, if you had a nice equal parabola, you would have two equal sides on both sides of the bisecting vertical line that would be presumably right here. Okay, so we should notice that. Well, what else do we notice? Well, we notice as it's climbing up, we notice that we should notice that vertical arrow, yeah, that guy, this vertical.
Dennis, can you stop in the office? Dennis, can you stop in the office?
Sorry about that. That vertical arrow is decreasing as up to the point that it reaches its maximum height. And as we can see right here at this guy, you should have noticed there is no upward. There is no arrow in the upward direction. That means that's the point at which it reached maximum height. Okay, so in this case, that would be at that point if you were measuring from here to here. When you're measuring from here to here, you'd have initial velocity, but you would have your final velocity would be 0. But then if you're measuring from here all the way down to where it hits the ground, your initial velocity is 0. God bless it. Your initial velocity is 0, while your final velocity will be whatever it is right before it hits the ground. Okay, and that should make sense because as you can see, after it reaches its maximum height, the vertical arrow increases thanks to gravity. Now watch the horizontal arrow. Horizontal arrow, as you can see, remains constant. It does not change because remember, we're forgetting air resistance, and this cannonball ain't hitting nothing. It ain't hitting nobody. So we're ignoring air resistance, we're ignoring friction, and we're going to say it's at a constant rate in the horizontal manner. Okay. There are other things you can notice. There's some time down here. There's also you can see actually the horizontal rate doesn't change, but the y does, or the velocity in the y-axis does change, whereas the x-axis velocity does not. All right, let's continue. Okay, so tackling projectile motion problems. So this is pretty much your walkthrough on how to answer these guys. So first read your question, okay, then reread it, and then list your givens and your unknowns. Ensure you divide your velocity into x and y components, okay? Choose one of the 5 kinematic equations discussed previously. So this is where we're going to be using the 5 kinematic equations like it's no one's business, okay? And then we're going to draw a quick sketch that gives you a better feel for the problem and it helps avoid careless mistakes. Plug your numbers in and solve. Okay, so like I said, I'm going to be skipping this guy, but please work on this on your own. I'm going to be posting a video walking through each of these, check your understandings. Try this on your own, see if you can tackle it, and then after you've done that, go check out the Check Your Understanding video. Same thing with that guy. Okay, so let's now talk about what I mentioned earlier, is that where we're putting an angle. This is what we call angular motion. Okay, we're going to talk about maybe shooting something upwards instead of horizontal, perfectly horizontal, perfectly horizontally. Whatever that English is hard, man. But we need to be working now with shooting things at an upward angle, maybe even a downward angle. Okay, so projectiles travel with a parabolic trajectory because the downward force of gravity accelerates them downwards from the otherwise inertial motion. But more importantly, that's not in here that I should have added, is the fact that because the downward force of gravity accelerates constantly or down, because the constant downward force, the equal downward force. So idea being is that from the moment, in this case, this cannonball is shot out within this image, from the moment it's shot out to the moment that it hits the ground, or right before it hits the ground, gravity is affecting it exactly the same, for the most part, exactly the same way. It's at 9.8 meters per second squared. Okay, exactly, for the most part, at least as far as writing it on paper and practicing, it's affecting that cannonball exactly the same way the whole time. Okay, so the horizontal motion of a projectile is independent of its vertical motion, and I've already talked about that before. Okay, and we've seen that in that cannonball imagery. Okay, so now we get another one. So the same kinematic equations can be used to analyze problems where the initial velocity is at some angle to the horizontal. Okay, whereas in your initial y velocity cannot equal 0. Okay, so this GIF is pretty good, showing a cannonball being shot out of a cannon at some upwards degree. Okay, kablamo, and then it's out, and then the same thing. There's that initial velocity, and it'll have its own special, thing. So just you wait. But notice that the x doesn't change, but the y does. Same difference. Now we're just adding angles to it. So the initial angular velocity, and this is going to be its sign. The initial angular velocity needs to be expressed as exponents and x-axis components and y-axis components. In order to find that, we need to do this. Okay, when we're given an angle, we need to solve it by more or less just SOHCAHTOA. So if we're looking for the initial x-axis velocity, it's going to be the angular velocity times the cosine of theta, whereas the y velocity, initial y velocity, is going to be the angular velocity multiplied by the sine of theta. Okay. So as an example, a rock is thrown with the vertical or with a velocity, an angular velocity of 3 meters per second at a 47-degree angle. Solve for the horizontal and the vertical velocities. So I'll just quick draw it on the side here. You should be able to do that. We're going to be using these right here. But, okay, so if we were to solve for the horizontal, well, that would be, there we go. It would be Vix is equal to, let's just plug it in. It'd be 3 times the cosine of 47. And then what you should get, just real quick, wherever my calculator went, what you should get is you should get, for the most part, just 2 meters per second. And more or less, you can either draw it like this, you know, in this direction, horizontal, whatever horizontal, forward, whatever, you know, it has to be. And then the y would be VIY is equal to the angular velocity, which again is 3 meters per second times the sine of 47. And there, it's going to give you a vertical velocity, initial velocity of 2.2 meters per second. In this case is going to be in the upwards direction because there is no indication that this is being shot below the horizon, that it's shot above the horizon. It's going to be 2.2 meters up. Now, we're going to get into, in the check your understandings, how to apply this, because that is not going to be, I'll just say that's not going to be the, that's not going to be true for the entire motion. So we'll get into how to solve for you know, the different y velocities. Okay. And then vertical displacements rely upon time, the angle, and the initial velocity. Height at different times relies upon a specific time interval or point in time. Okay, so that means, remember, when we start the motion vertically, okay, even though it's being obviously shot at a particular angle, so it's not being shot straight up, that's your initial velocity that you'll have after you solve for your initial y velocity. But eventually, it's going to reach 0 because it's reached the top and it's reached the maximum height in which it can move. So your final is going to be 0. But then so you can find a time interval from the time it shot out to its maximum height. But then what you have to do is you have to find the time. You have to find the time interval between its maximum height to the point in which right before it hits the ground. Okay, where your initial for that one will be 0, and then your final is going to be whatever you calculate. So as an example, an object is fired from the ground at 100 meters per second at an angle of 30 degrees. How high is the object at 2 seconds? Now for this one, okay, because I think I've got this, it's this and then that. And we're already running a little longer than I was hoping. This one, I will only solve this. I won't solve this one in the video. Try this on your own. If you have a question on how to solve this one, or email me, text me on Remind, and I'll help you out with that one. But we should be able to solve this one now that I did the other one, or at least we'll see if you can. Okay, and then last slide. Okay, so maximum height relies upon this idea, and I just mentioned this. It relies upon the idea that your final y velocity is going to be 0 meters per second. Okay, since it is no longer moving upwards at that time. So again, here's another example. Solve this one on your own, and then after that, then go and watch the video, or then do the check your understandings. So here are the check your understandings. Okay, real quick. So these are going to be pretty busy. Again, I'm going to have a separate video walking through how to do all these. Okay, so those are the notes. So that's it. If you still have any questions, maybe there's some I glossed over, went over too fast, go back, watch the video again. If not, if that doesn't help, email me, text me, and I'll try to help you out the best I can. So, all right, guys, I'll see you in the next video.